Hello, this is Minji Lee from Seoul National University. I will present about interactive real-time simulation of robotic snap connection process. Snap connection is a process connecting two objects into tight complementary geometry by exploiting deformation of deformable objects and is utilized in various industrial sites. For automation of these processes, simulation of the snap connection is necessary. However, the simulation is challenging for three reasons. Firstly, the snap connector has high stiffness and lightweight, which leads to large dynamics discretization error when any nonlinearity is included in the dynamics. In addition, to simulate fast snapping motion, a noticeably small damping is required, and for these reasons, the simulation becomes unstable. And finally, the deformable object has high dimension, which makes the simulation slow. Recent studies related to FEM simulations typically rely on iteration-based implicit Wheeler integration, which induces undesirable numerical damping and cannot simulate fast motions, whereas semi-implicit Wheeler integration is only conditionally stable. Also, in case of inversion-based simulations, model reduction is essential, and for this, a prior simulation or experiment is required. Therefore, existing simulators are inappropriate for snap connection simulation. In this paper, we developed real-time simulation framework of snap connection, which satisfies discrete time passivity. It does not require a priori simulation, and physical accuracy is validated with experiment. To achieve this, we approximated time-consuming complex collision detection process into simple MLP traversal and utilized GPU to enhance the simulation speed. As the position on the FEM surface is given as input, penetration depth is computed after traversing the network, and normal vector is calculated from the differentiated network. Also, we reduce the dimension of the dynamics of socket connector to speed up the simulation. Firstly, we segment the original linear FEM into one segment with contact and others without contact, and connect them via strong spring. Then balance model reduction is applied to each segment to further reduce the dimension. Balance model reduction is an analytical technique which does not require any simulation or experimental data. However, since coupling terms are still remaining, each equation cannot be solved separately. To circumvent the problem, we analytically eliminate the coupling terms via short complement. With contact force calculated from original FEM, we can solve dynamics of each segment in parallel. Also, every matrix used for calculation can be pre-calculated. This figure shows three different snap connectors, which are segmented into two segments. After segmenting and applying BMR, the dimension has reduced drastically. If nonlinearity is included in dynamics, discretization error is inevitable. Especially for high Young's modulus, it induces severe instability as shown in the figure. On the other hand, our framework satisfies discrete time passivity without any artificial damping while applying techniques to enhance speed. As a result, we can overcome the challenges mentioned above and stably simulate even with stiff material. Also, it can generate fast snapping motion as it can be simulated with small artificial damping. Additionally, it makes it able to use high spring coefficients to guarantee strong connectivity between segments and reduces discrepancy from the original problem. We validated the accuracy of our framework by comparing the reaction force with that of the experiment. As a result, RMS error of the force was 4.9 Newton, and the frequency has improved about 8.5 to 9.5 times from the baseline simulator. Also, we tested the framework with various geometries and material parameters, and it could robustly simulate different snap connectors. Thank you for watching.